All right, hello. We're coming to the end of our little mini unit on stoichiometry, and you have a quiz this Thursday on everything that we've looked at so far, which also means that you have a fun unit test that's just around the corner. But right now, let's look at our new topic today. There's not a lot that's new in it in terms of mathematics. So if you feel fairly confident with the mathematics that you've been doing already with stoichiometry, it's not that much different. There's just an extra step. You need a little bit more stamina to do some of these problems. So we are going to start looking at, and this is, can I read and do it? So this is limiting, this is all about limiting reactants. Limiting reactants or limiting reagents, right? So just to review so that we're sure, we have some reactants on the left side of your chemical equation. They come together and they make some products. Okay? Now the thing about a limiting reactant problem is one of the reactants is going to determine or limit how much product that we can make. So one is going to restrict the amount of product that we can make. So if we just use a simple analogy from cooking, if we say that, it's like 2 hamburger buns plus 1 piece of meat or 1 patty plus one piece of cheese, and that will give us a delicious hamburger. Okay? So there's kind of our chemical formula for making a hamburger. Now, say I have a problem where I'm given 6 buns, and I'm given 2 pieces of meat, and I'm giving 2 cheese. Okay? Or I'm given 3, let's say 3 cheese to make it better. And then I want to determine, right? So I want to know how, if I have this many ingredients, how many hamburgers can I make? I want to make the maximum number of hamburgers I can, given the ingredients that I have. So let's start. So if I've got 6 buns, and then I know from my equation here, 2 buns then gives me 1 hamburger, and I get this from my equation. So if I do that, that's like buns cancels out, so I'm left with hamburger. So that will give me 3 burgers that I can make maximum, given the fact that I've got 6 buns. Okay, I can do the same thing with cheese. So I've got, or meat, sorry. 2 meat times, my equation tells me I need 1 meat or 1 hamburger. So meat cancels, I'm left with hamburger, so that tells me I can make 2 burgers. Okay, if I have 2 meat, I can make 2 burgers. Okay. 3 cheese. 1 cheese, and our equation says, yes, I've got 1 cheese, and I want to make 1 hamburger. Cheese cancels. I can make 3 hamburgers, 3 burgers. Okay? So the maximum, if I have 6 buns, the maximum amount of hamburgers I can make is 3. If I have 2 meat, the maximum amount of hamburgers I can make is 2. And if I have 3 cheese, the maximum amount of hamburgers is 3. But I only have 2 meat, so I can only really make 2 burgers. The lowest amount is going to be the maximum amount I can make. Right? So if I have 2 burgers, right, that means I would need to have 4 buns. Right? So I still have 2 buns that would be left over, so that's okay. If I make 2 burgers, I need 2 pieces of cheese. I'd still have 1 piece of cheese left over. Okay? So that would work to make 2 burgers. For making 3 burgers, though, using all the buns, I would need, according to my equation, I'd need 3 pieces of meat. But I don't have 3 pieces of meat. I only have 2 pieces of meat. So I can't make 3 burgers. With the cheese here, it says we could also, if we used all the cheese, make 3 burgers. But, again, do I have enough buns to do it? Yeah, I would have enough buns to do it. But I wouldn't have enough meat to do it. I only have 2 meat. I would need 3 meat to make 3 burgers. So the maximum number of burgers I can make is 2. And then meat becomes, in our equation back here, meat becomes what we call the limiting reactant, LR, the limiting reactant. Okay? So this same sort of logic works for these questions with the chemical equations. So let's do a couple of different ones so you can see a variety. I'm not going to do them all because you need to hand this in, but hopefully help you out. So our first example is if 50 grams of, this is potassium chloride, reacts with 50 grams of diatomic oxygen gas to produce potassium chlorate according to the following equation, how many grams of potassium chlorate will be formed? So, we need to have an equation to start off with. And so it's telling me I've got potassium chloride. I'm going to guess that's a solid plus O2, which is a gas. And I'm going to make potassium chlorate. Potassium's got a charge of +1, chlorate's got a charge of -1, so that's fine. 1 potassium, 1 potassium, 1 chlorine, 1 chlorine. 2 oxygens, 3 oxygens. It's not balanced. Remember, this is the most important part because we need to use the mole ratios from a balanced equation to get the stoichiometry to work. So if our equation is not balanced at the beginning, the whole problem is messed up right from the start. But 3 and 2, we've done enough of these. I hope you're thinking 6. So I'm going to put a 2 here. I'm going to put a 3 here. So I've got 3 oxygens. So I've got 6 oxygens. And I've got 6 oxygens. But now I've added an extra potassium and an extra chlorine. So I'm going to need to put a 2 in front of there to balance that out. Okay, so that's nicely balanced. Good. All right. So start with what you have to what you want. What do I have? So it's telling me I've got 50 grams of this, and I've got 50 grams of this, and I want to know how many grams of potassium chlorate. Now, the trick is some of these questions will also ask you what is the limiting reactant. And sometimes we can get confused by this and just say, well, look, the one with the smallest number has got to be the one that's limiting. Don't fall for that trick because that's not always the case. You really need to do the stoichiometry in the math to determine which one is the limiting reactant. So you need to, if you're going to do this, you need to do 2 mass calculations and compare the results. So let's see how much we can do. Our first one, if we've got 50 grams, we've got 50 grams of potassium chloride. How many grams of potassium chlorate can I make? So 50 grams times 1 mole KCl over grams KCl, and I need 2 grams of KCl. I need to go to my periodic table. Potassium is, and since this is a rough comparison, I'm not going to worry too much, it's 39, and chlorine is 35.45. That gives me 74.45 grams of potassium chloride. What I'm going to do now need to relate moles of potassium chloride to moles, potassium chloride to moles of potassium chlorate. Remember, this is called dimensional analysis, right? This is dimensional analysis. So you need to use each step. You may say, well, mathematically that doesn't need to be there because you're just multiplying by 1. But it's good practice, it's good habit. If you are doing dimensional analysis, which is what this question asks for, you need to include every step. So even though mathematically you're multiplying by 1, it doesn't make any difference. To set the question up correctly and to make sure that all the units cancel that you don't want, and that's the purpose of dimensional analysis, that you include this step. Okay? All right, so now I'm going to 1 mole potassium chlorate, and I need the mass of potassium chlorate. Mass potassium chlorate, potassium 39 plus 30.5. That works out to 122.45. And so I can see that I've got grams of potassium chloride, that cancels. Moles potassium chloride, that cancels. Moles of potassium chlorate and moles of potassium chlorate, that cancels. So my answer will be grams of potassium chlorate. Okay, so your trusty calculator out. So I do 50 and I say divided by 74.45, it equals, and then this point I have it on my paper, so that's fine, but I know mathematically it doesn't mean anything, so I'm not going to worry about it. So I'm just going to multiply it by 122.45, and that gives me 82.24 grams. Okay. Is that how much that we can make? Maybe. But we're also being told that we're given a certain amount. We're also told we're given 50 grams of diatomic oxygen gas. So we need to see if we use up all the oxygen gas, what's the maximum amount of potassium chlorate we can make. So we have to do another calculation using the oxygen. So 50 grams of O2 multiplied by 1 mole O2. And remember, this is diatomic, so that's 16 twice, so that's 32 grams of O2. Now compare moles of O2. 3 moles O2 to 2 moles KLO3 times 1 mole KLO3 times 122.45 grams KClO3, and that equals 50 divided by 32 multiplied by 2 divided by 3 times 122.45. That gives me 127.55 grams KClO3. So, what is the amount that we can make? Well, it's the amount that's the least amount. That's the maximum amount. Okay, these things are going to react together. Okay? So what this tells you is that the KCl in this equation is going to get used up first. Okay? Once it's gone and it's all been used up, there's going to be some oxygen that's left. Okay? But that's also going to determine then how much potassium chlorate that can be made. So in this case, your potassium chloride is our limiting reactant, and just as a sneak preview for our next part, the oxygen is going to be called, it's the excess reagent or the excess reactant, meaning that this is going to be left over. There's still going to be some that's left there. In this equation, you let it go, all the potassium chloride is going to be used up, but there's still going to be a little bit of oxygen gas that's left over, right? We know if we used up all the oxygen gas that was there, we could make 127. But we can't do it because the potassium chloride is going to run out first. So the maximum amount we can make is 82.24 grams. Okay? Those other ones are about the same. Same. Moles. Okay. Let's do this one because it gives us a nice, it's talking about volume of a gas at STP. Now remember for this that it has to be STP. Right? What's STP? Standard temperature and pressure. Standard temperature and pressure. So we're talking about 0 degrees and at one atmosphere. If that's the case, that was that Avogadro that determined that, then we can know that at STP, 1 mole of a gas will occupy 22.4 liters. Any gas. Okay? It's a magical amount. So we can relate then moles of a gas to volume as well, which is important for these. And that's what we want to know. So we're given our equation here. It says if 13.5 liters of nitrogen gas reacts with 17.8 liters of hydrogen gas at STP, it must say that. That's a good way to get tricked. If not, you can't use this. It has to be at STP. According to the following reaction, what mass of ammonia, it's ammonia, don't get confused. Ammonia, it's ammonia, ammonium is NH4+. Ammonia would be produced. Okay? So again, we need to see what's the maximum amount. So we have to go through each part. So we're being told, and sometimes I like to write it underneath what I'm being told. I've got 13.5 liters of nitrogen. I have 17.8 liters of hydrogen gas. And I want to know what mass. Mass is in grams. So we're going to have to make sure. We don't want to know the volume. We don't want to know in liters. That we want to know in grams. What that will be. Okay. All right, so start with what you know, what you have, to what you want. What do I know? So I'm going to start with this one. So I've got 13.5 liters of N2. It's at STP, so I can relate 1 mole of N2 to 22.4 liters. See, of N2. See, I've canceled out. I'm not dealing with liters anymore. I've changed the problem to talking about moles. Okay. Next, I want to relate moles of N2 according to our equation. So I've got 1 mole N2 to moles of ammonia. So that's 2 moles of ammonia. Okay. Finally, very easy, I can relate moles of ammonia, 1 mole NH3. I can relate that to mass grams of ammonia. So The mass of nitrogen is about 14. The mass of hydrogen is 1. So that would be a mass of 17 grams. Okay, just to make sure, liters N2 cancel. Mole N2 cancel. Mole ammonia cancel. I'm left with grams of ammonia, which is what I want. Okay, so I've got 13.5 divided by 22.4 equals, multiplied by 2 equals, multiplied by 17. That tells me, if I use that up, the maximum amount of mass, 22.49 grams NH3. Remember to include units and what you're talking about in the end. And also, I kind of like things in a box. Okay. That's nice. But we're also given a mass of hydrogen gas. So let's calculate it for hydrogen. So let's see, I've got 17.8 liters of hydrogen gas. We're at STP, so I can relate 1 mole of hydrogen gas to 22.4 liters hydrogen gas. And then 1 mole of, no, I don't have 1 mole, Mr. Harrison, I have 3 moles of hydrogen gas, 2 moles ammonia, multiplied by, and I know it's 17 grams to 1 mole NH3. Okay, let's see. 17.8 divided by 22.4 multiplied by 2 divided by 3 divided by 7. That tells me I can make about 9 grams NH3. So, when we compare them, the smallest one is the amount that I can make. Okay, I can't make any more. Okay? So this is a case in which the maximum amount I can make, the answer is I can make 9 grams of ammonia. Okay? This is a case even though we start with a higher number, a higher volume of hydrogen gas, but in the end, it's the one that's the limiting reactant. It limits how much we can make. Okay, the hydrogen gas is going to run out first. Okay. Want to do this one, this last one? One more, that's it. This one has formula units or atoms. So for this one, we need to remember that Avogadro's number, 6.02, multiplied by 10 to the 23, this ungodly number, it can stand for atoms, molecules, or what's called formula units, or sometimes just written FU, okay? So there's this many, which is a huge amount. That's why we don't usually talk about it. Like, how many atoms does a chemical reaction make? It's just the number is so huge, it's not worth talking about. But there's this many in 1 mole of anything. Okay. So that's what we need to know, because this problem tells us how many molecules, or no, how many atoms of iron are going to be reacted. Ooh, this one's got formula units, and it's got volume as well. So it says if 3.18 times 10 to the 23rd atoms of iron react with 67.2 liters of chlorine gas at STP, that's important, remember, it has to say this because we'll be using our 22.4 liters per mole at STP. Okay. What is the maximum, oh boy, now we got to convert it to grams. What is the maximum number of grams of iron 3 chloride that can be produced? The nice thing is that they balance the equation for us, so at least that piece of work is finished. Okay, so let's start with the first one. So I have 3.18 multiplied by 10 to the 23rd atoms of iron, right? Always what you have to what you want. Okay, I know 1 mole of iron is equal to Avogadro's number, 6.02 times 10 to the 23rd atoms Fe. Okay, that's converted into moles. Remember, I want it in grams. So now I want to cancel off. I've got 2 moles iron and 2 moles, what is that? Iron 3 chloride. And I want it in grams. 1 mole iron 3 chloride. There's grams of iron 3 chloride. That's going to give me an answer in grams of iron 3 chloride. Let's see, iron 3. One 162. Then it's always a big thing. Can I use my calculator properly? So 3.18, and then I think I need to shift 10 to the 23rd divided by 6.02 to the 23rd. So that looks right. Multiplied by 162.145. So assuming it's all correct, I get 85.65 grams. That's if I do that one. Okay. Not done. Got one more. So this one, I want to look at the chlorine gas, and I've got 67.2 liters of chlorine gas. 1 mole of chlorine gas at STP is equal to 22.4 liters of chlorine gas. And 1 mole, no, careful, 3 moles chlorine gas. 2 moles iron 3 chloride. By 1 mole iron 3 chloride, grams iron 3 chloride, 162. Just check. So liters chlorine gas, mole chlorine, mole iron 3 chloride, mole iron 3 chloride, grams iron 3 chloride. Okay, so let's see. So we got 67.2 divided by 22.4 equals, multiplied by 2 equals, divided by 3 equals, multiplied by 162.145 equals, I get 324.29 grams. So again, we can only make the maximum amount. So, given this many atoms, this is what we can make. Okay? Again, this math, we should be able to do it by now. It's just practice, but please use the dimensional analysis because it helps you keep track of all the units and making sure that all the units are canceled out. But again, you need to start with a balanced equation. You always need to work with what you have, what the question gives you, to what you want. Always make sure that you've got all the units in the question and that you've read it to make sure that you've got the answer, because it could, a lot of times we want to know about grams, but it could ask you questions in how many liters, the volume, or how many atoms, or formula units, all of these sorts of things. Okay? Practice, practice, practice. Let me know if you need any help.